this module, you will learn about various forms of energy, the possible conversion from one form of energy to another, law of conservation of energy and power. Some forms of energy that we will deal with in this module are heat energy, chemical energy, electrical energy, and nuclear energy. Now, let's understand heat energy first. When satin cloth pieces are rubbed against each other, due to friction, sufficient heat is produced to make the hands feel a rise in temperature. The rise in temperature is due to the rise in internal energy of the body. Here, the satin cloth pieces. Consider that a body is given a push and is then released. When it comes to rest, all its kinetic energy is lost, and a part of this kinetic energy is converted into heat, and the remaining is lost in doing work against the friction. To overcome friction, there is a slight rise in the temperature of the surfaces in contact. Let us look at another form of energy, chemical energy. Chemical energy is produced when the molecules of the reactants participating in a chemical reaction combine to attain greater stability by forming stable compounds. The burning of any form of fuel is a chemical reaction. Burning is an exothermic chemical reaction where the chemical energy of the reactants is mainly converted into heat energy, which can later be manifested in other forms. Thus, in an exothermic reaction, the energy of the reactants is greater than that of the products. Hence, exothermic reactions like combustion of fuels are indispensable in catering to our daily energy needs. There are some other chemical reactions that absorb heat during their reaction and are called endothermic reactions. Some reactions, such as photosynthesis, are endothermic reactions which allow plants to make sugar from carbon dioxide in the presence of air. Chlorophyll acts as a catalyst in the process of photosynthesis. In this case, the energy required for the reaction comes from sunlight. Now, let's understand electrical energy. Electricity is the most convenient form of energy. Electricity is a manifestation of electrical energy and is responsible for running many of the devices in our daily lives, such as electric bulbs, fans, grinders, etc. Till the late 19th century, physicists were of the view that the mass of an isolated system remains constant and it is conserved. They believed that matter can be neither created nor destroyed. It can only change from one form to another. For example, when water is frozen, it turns to ice. The ice melts to water, and when water is heated, it turns to vapor. In all the three forms, the mass of the system remains the same. However, Albert Einstein proposed his famous mass-energy equivalence relation. E is equal to mc square, to show that mass and energy are equivalent. In this relation, E is equal to mc square, and c is the speed of light in vacuum, which is approximately 3 × 10⁸ meters per second. Thus, according to Einstein's mass-energy equivalence relation, mass and energy are equivalent to each other. Mass can be converted into energy and vice versa. When a mass m is destroyed completely, the equivalent energy E is produced. Thus, according to Einstein's mass-energy equivalence equation, 1 kilogram of matter can produce a humongous amount of energy, which is E is equal to 1 × 3 × 10⁸ square joules, equal to 9 × 10⁻16 joules of energy. The energy produced by 1 kilogram of mass is equivalent to the annual electrical energy produced by a power generating station, that is 3000 megawatts. Now, if 1 gram of mass is completely destroyed, the energy produced is expressed as E is equal to mc square, that is equal to 0.001 × 9 × 10⁻16, that is equal to 9 × 10⁻13 joules. One of the most expensive forms of energy is nuclear energy. Nuclear energy is energy derived from a nuclear reaction, such as nuclear fusion or nuclear fission, from which energy may be released in accordance with Einstein's mass-energy equivalence relation. In nuclear fission, a heavy nucleus like uranium-235 absorbs a slow neutron and hence splits into lighter nuclei. The final mass of products is observed to be less than the total mass of the reactants, and this difference in mass is known as mass defect, denoted by delta M. The mass defect delta M is converted into energy in accordance with E equal to delta M into c square. In a nuclear fusion reaction, lighter nuclei fuse to form a heavier nucleus. This fusion is accompanied by the release of a large amount of inherent energy in accordance with the mass-energy equivalence relation. In nuclear fusion too, there is a mass defect which accounts for the amount of energy released according to E is equal to delta M into c square. The source of the massive amount of energy released by the Sun and the stars is believed to be due to a nuclear fusion reaction, when isotopes of hydrogen, namely deuterium and tritium, undergo fusion to form an isotope of helium and a neutron with the release of a large amount of energy. The energy released is due to the conversion of a mass defect between the reactants and products in the reaction. The law of conservation of energy states that the total energy of an isolated system is always conserved and that energy can only be transformed from one form to another, but can neither be created nor destroyed. For example, when a firecracker explodes, the chemical energy stored in it is converted into light, heat, and sound energy. Nuclear energy is used to produce electrical energy in a nuclear reactor. Different forms of energy are used to do work. Earlier, we learnt that work is said to be done when a force F acting on a body displaces the body through D in the direction of the force. When work is done, energy is transferred. The rate at which work is done or energy is transferred is called power. Thus, power P is equal to work done W by time T. Instantaneous power P is equal to dW by dt. But dW is equal to F dot dr, where dr is the displacement. Therefore, P is equal to F dot dr by dt, which is equal to F dot V, since dr by dt is equal to instantaneous velocity v. Power is a scalar quantity and its SI unit is watt, and its dimensional formula is m power 1, L power 2, T power minus 3. Power can be expressed in horsepower denoted as HP, and 1 horsepower is equal to 746 watts. The commercial unit of electrical energy is kilowatt hour denoted as kWh. 1 kilowatt hour is equal to 1000 watt into 1 hour, and which is equal to 1000 watt into 3600 seconds, and is equal to 36 into 10 to the power 5 joules. You have now reached the end of this module. In this module, you learned that some of the different forms of energy are heat energy, chemical energy, electrical energy, and nuclear energy. Chemical energy is produced when the molecules of the reactants participating in a chemical reaction combine together to attain greater stability by forming stable compounds. Albert Einstein showed that mass and energy are equivalent and are related by the relation E is equal to mc square, where c, the speed of light in vacuum, is approximately 3 into 10 raised to 8 meters per second. Nuclear energy is the energy derived from the nuclear reaction, such as nuclear fusion or nuclear fission, from which energy may be released in accordance with Einstein's mass-energy equivalence relation. Law of conservation of energy states that the total energy of an isolated system is always conserved, and that energy can only be transformed from one form to the other, but can neither be created nor destroyed. Power is defined as the rate of doing work. Power is a scalar quantity, and its SI unit is watt, and its dimensional formula is m power 1, L power 2, T power minus 3.